Hello everyone. So, we will continue our discussion on X-ray diffraction. Yesterday we were discussing qualitative phase analysis. How can you use X-ray diffraction pattern to qualitatively analyze your sample? What do we mean? Idea is to find the phases present in your sample. And how do we do this? We already know that we have a database where we have the information about each phase, right. So, you compare your pattern to that database and see if there are phases from that database present in your sample. So, few things which we have to keep in mind, that's what we were discussing yesterday. So, I mean these are the softwares, and for your assignment you will be using HighScore Plus, which is available in our lab. So, we were talking about peak position and intensity, right. That is very important. You have to match the peak positions, right. Also important is intensities, right. So, we saw one example where we had a bad match. Why? Because according to the reference the reference peak, you should see strong peak here, right. Although the peaks are matching, like here you see there is some match, but here this is the third strongest peak, you do not see any match. So, that means there is a problem. So, these things you have to always check when you do qualitative analysis, right. Do not rely on just one peak, okay. Another thing, that is where we stopped. Today we will start with this sample displacement, right. Why does it occur? See, now you are familiar with X-ray diffractometer. Basically, you can think of it as you have a sample here. This is like a para-focusing geometry. Basically, you have a detector. No, sorry, this is the X-ray tube. Let us say tube, and here you have a detector, and here you have a sample. So, the way it works is, right, this you remember, right. So, we said that the tube and detector will rotate, right. In some cases sample also can rotate when tube is fixed, but the idea is this is the sample is always the focus or at the center of the circle, right. So, when there is some displacement, suppose sample is bit down or sample could be up, sample displacement will cause this. If there is this sample displacement when it is not in the focus, okay, that may cause the sample displacement. So, what you will see then is that your peaks have been shifted by equal amount, right. See, in this case peaks are close, peak that are close together should be shifted in the same direction. So, you see like your peak in the pattern has shifted in this direction, right. So, I mean red one is the reference pattern standard, right, which you get from ICDD, okay. What do you see? There is a constant shift. So, that tells you that it could be because of sample displacement, okay. And how you can quantify it? Using this formula, right, minus 2s cos theta over r. R is goniometer radius. We are talking about this. So, this is the radius r, right. So, depending on the sample displacement s and angle theta, you can calculate what will be the sample displacement, okay. So, it is easy to check when you are looking at like maybe 3 peaks, strong peaks, and you see a constant shift, or maybe if you compare 2 different phases, all peaks are shifted by equal amount, that tells you that there is an issue with sample displacement. Okay, so now the question comes, once you have identified these phases, suppose you have 2 phases in your sample. In this case, you see your sample is made of Al2O3 and TiO2, right. Can we relate these relative phase intensities to relative amounts? Often this is the question we ask, right. We always want to know which how much of each phase you have, right. So, can we do this? What do you think? What do you think here just by looking at the peaks? So, this is the TiO2 strongest peak, second strongest, third strongest, right. Al2O3 is here, right. Just by looking it is not possible, you cannot relate your phase intensities to phase amounts. In this case, actually this is 50% TiO2, 50% Al2O3. Just by looking at plot, can you tell? No, because it will depend on the phase. The TiO2 pattern is more intense, right. You see the TiO2 pattern is more intense because it diffracts X-rays more efficiently compared to Al2O3. So, it depends on the type of phase you are looking at. You can't just by looking intensity, oftentimes people make these mistakes when they just compare the amounts based on the intensity, okay. This is one example. But when you do proper calibration, so with the proper calibration, maybe the amount of each phase present in the sample can be calculated. You will have to do proper calibration, okay. We will come back to that, how to do quantitative analysis. When you want to do quantitative phase analysis, we will have to do some calibrations, we will talk about it. So, now the question comes, we do not know how to do quantitative phase analysis, right. We know qualitative phase analysis. Qualitative phase analysis means you know what are the major peaks present in your sample. You can do that using any software, okay, and that will be part of assignment also, where you will be using HiScore Plus software to identify major phases in given diffraction pattern. So, obviously the second question comes like how do we quantify the phases, that is very important, right. When we are talking about phase analysis, like once you have identified the phases, it is very important to know how much, right. So, that will be discussed in this lecture. So, there are few different ways to do quantitative phase analysis, okay. We will start with external standard, then we will talk about internal standard, and then we will talk about Rietveld refinement, which is most commonly used these days, it's quite popular, okay. So, but we will go over other methods also, right, like external standard and internal standard. So, how do we do it? So, let us look at the external standard method, right. What do you get from the name external standard, right. So, you are using a standard externally, right, simply if you look at the name of the method, right. So, basically what it does is the diffraction intensity of a phase is compared against the diffraction intensity of a pure phase. So, suppose you have a mixture of alpha and beta, simple example. Now, you are comparing the intensity in your sample like alpha intensity to the intensity of alpha in pure alpha phase, right. Suppose you do X-ray diffraction of pure alpha phase, you will get lot of peaks. You just look at the strongest peak. So, this is about comparing what is the intensity of that particular HKL in pure alpha phase versus what is the intensity of HKL in your mixture, alpha phase in the mixture. Got it? Got the idea? How do we do it? We all have seen this, again we will come back to it, right. You all know the famous equation, how do we calculate intensity of diffracted beam? We are coming back to that because it is very important. So, I, right, that is 2, you have calculated this structure factor, then let us see multiplicity factor, right, then you have a Lorentz polarization factor, right, then you have absorption factor, then you have temperature factor, okay. So, we can also write it as over mu, where 1 over 2 mu is basically absorption factor. Absorption will depend on your absorption coefficient simply. If you have a very that will affect your diffracted intensity of diffracted beams. For example, if you have very high absorption, then the diffracted intensity of diffracted beam will be low, right. So, this is the absorption coefficient and this is the temperature factor, but let us focus on the, so this we can write intensity as, right. So, what do you see here? So, for a particular phase alpha, right, we are talking about binary system where we have alpha and beta. We want to know how much of alpha, how much of beta. So, I alpha, right, can be written as, now this is for the pure substance, this equation is for pure substance, right. So, this intensity times C alpha. Suppose you know the volume fraction of alpha phase, right, or even if you do not know, you can write it as C alpha, right, because if C alpha is 1, that means you should get the intensity like this, right, this is for pure phase. So, we are multiplying this, and this all we can write, this will be constant, right, because we are talking about one HKL, one plane for an example, right, strongest peak for example. So, I alpha can be written as K1 C alpha over mu m. What about mu m? Now, mu m is the absorption coefficient of the mixture. You see this term is appearing here, mu. So, we are talking about, this is the absorption coefficient of mixture. If it was a pure phase, then it will be mu for that pure phase. You understand, right? So, volume fraction and these terms appear, rest you can write it's a constant. Now, this we are not going in detail, but you can refer to the reference to go through the calculations, but idea is you have to write how do you relate the absorption coefficient of the mixture, which is mu m, to the volume fraction of each phase and mass absorption coefficient of each phase. Okay. So, it can be written as, so first of all, what is this equation? This equation is nothing but it is a weighted average. So, mu m over rho m is the mass absorption coefficient of mixture is weighted average, like so weight of alpha times mu alpha over rho alpha is mass absorption coefficient plus weight of beta times mass absorption coefficient for beta. Okay. Because your mixture is consisting of alpha and beta phase, right. So, basically what we can get is, we are not going in detail, but you can refer to the reference. We can relate this intensity. So, this is the intensity of alpha phase in a binary mixture I alpha. This is the intensity of alpha phase, intensity of the pure alpha phase. So, I alpha over I alpha p can be related to W alpha, this is the weight fraction of alpha times you see mu alpha over mu beta. So, this is the expression over W alpha mu alpha rho alpha minus mu beta rho beta plus this. So, this is the expression what you see here. So, we have found a relationship where we can relate this intensity, ratio of intensity to the weight fraction of alpha. Alpha is the standard, right, we are talking about external standard, and we have to also know absorption coefficients, very important, alpha, mu alpha and mu beta, right. So, if you know mu alpha, mu beta, and we can then calculate the fraction W alpha, if you know I alpha over I alpha p. So, what you can do, suppose in this case you see some examples, right, if you look at the plot. So, this curve, let us see lower most curve was derived for quartz potassium chloride mixture. So, quartz is here external standard, okay. So, mixture of quartz and potassium chloride. So, what you see, we can vary the amount of quartz, right. So, depending on the weight fraction of quartz, what you see the relationship, then I alpha over I alpha p, right, we got these data points. So, this is first of all what you notice, this is not a linear curve, right, this is not a linear curve, but remember when your mu alpha becomes mu beta, suppose you have two phases where your absorption coefficients are same, what will happen, this term will become 0, it will be directly proportional to W alpha, right, then it will become linear. So, it depends on the absorption coefficients of your phases, right. So, if you have developed these kind of calibration curve, now depending on the intensity, right, you know how much intensity you have in your sample, right, and depending on this ratio you can calculate what will be the weight fraction. That is the idea. You are interested in the weight fraction, right, of, if you know the alpha you can calculate the beta, that is the idea. So, it is the external standard where we are comparing the intensity of a phase against the diffraction intensity of a pure phase. Okay. Now, we will come to internal standard, right, internal standard. Now, we are talking about standard which is used internally, which we can use to spike the samples, right? We can add into sample, right. Then you can understand the difference between external and internal. So, here we are mixing standard with your sample, right. So, in this method a diffraction line from a phase being determined, right, which we want to know determine, is compared with a line from a standard substance mixed with sample in known proportion, but in this case you know how much you are adding. So, you know the standard, you know how much you have added in your sample. You have a sample, suppose alpha plus beta, and you know you are using a standard S, right, and I am using 10% of S. So, you added 10% of S in your sample. So, you know the 10%, right, but it is mixed with the sample, that is why it is called internal standard, right. So, again we come back to the intensity equation. See, this equation is very important, I mean now and then we use this, right. So, again once you have added standard to your sample, you can write again the intensity equation IA as, again this constant K3, the volume fraction of your alpha phase for an example, or A phase here, let us see A phase in that mixture over mu m, right. Is it clear how it is the same as what we did last time, right. But we are looking at one phase, we are looking at the intensity of A for an example. Okay, you have a mixture of like A, B, C, D, it is like this. Okay, you have so many different phases, and now you are adding S, right. That is what we did internally. Why we call internal standard? Because you already have, suppose 4 phases A, B, C, D. Now you are adding S. Now we are focusing on the, so what is the volume fraction, right. So, suppose the volume fraction of A in this mixture is C prime A, that is the idea, right. See, the volume fraction of A in A, B, C, D will be different. Actually ideally what we want to calculate, we want to calculate WA, right, because we know this mixture A plus B plus C plus D. We want to know WA, WB, WC, WD, that is what we want to calculate. Is it clear? But how we are doing it? We are now taking a standard, adding it with ABCD, right. Now this fraction, so now if you have to focus on the intensity of a line, we are talking about the strongest line. Again we will come back to it, this IA, what do we mean by IA? It is not just the height, it is the integrated intensity. So, in these calculation wherever we are using intensity, that is integrated intensity. What does that mean? It is the area under the curve basically. Okay. So, you know that you have this peak, calculate the area under the curve, that will give you integrated intensity. So, IA, so this is clear. Similar thing we can write for standard also, right. IS is the intensity of the strongest peak of standard, will be K4 times CS over mu m. So, mixture will be same, right, because this is the mixture A plus B plus C plus D plus S, same mixture, right. So, only difference will be CS, CS is the volume fraction of your standard. Okay. Now, what about the ratio? If you calculate the ratio I over IS, what do you get? C prime A over CS, right. It's just simply you have to put mu m will get cancelled, clear. What is C prime A? C prime is like a volume fraction, right. Volume fraction, how do you calculate? Volume of A over total volume. Volume of A will be weight of A over density of A. right, W prime A over rho A. Why we are using W prime A? Because now your mixture is consisting of A plus B plus C plus D plus S, not A plus B plus C plus D, right. So, this is straightforward, right. So, now if you combine 1 and 2, what do you get? You will get IA over IS is equal to another constant, you know, because you have to all K3, K4 are constant, you can reduce it, and basically you get a relationship in terms of W prime A, which is the weight fraction of it. And this weight fraction of A depends on this, it is equal to WA times 1 minus WS. That means, if your WS is 0, your W prime A is WA, right. When there is no standard, your W prime A will become W, and when your WS is equal to 1, then 0, right. So, but WS you know, interesting, good, I mean you know the how much internal standard you have used. So, when you replace this W prime A with WA times 1 minus WS, what, so you get constant times WA, because you know all the other things. So, you have now the relationship where your intensity ratios are directly proportional to WA, right. IA over IS is equal to Ks times constant times WA. What does it tell you? It is a linear relationship. So, you can plot in this case, what is this? The calibration curve for the quartz with fluoride as internal standard. You can get IQ over IF, and as the weight fraction of quartz varies. So, you can get these calibration curves, then based on the intensity what you have in your sample, you can calculate how much of quartz in this case, because right we use the fluoride as internal standard. So, these are few methods which you can use to determine the phases, okay. And again I will so calibration curve can be prepared from measurements on a set of synthetic samples containing known concentration of A and a constant concentration of a suitable standard. So, you have to identify the suitable standard. In this case you see here fluoride, okay. And again the intensities we are using here are integrated intensities. Basically it is the integration like area under the curve. So, you have a peak, diffraction peak, you calculate the area under the curve, will give you integrated intensity.